Very good morning, dear students. I hope all of you enjoyed the session on second law of thermodynamics. Today, we will learn the very important topic, the Carnot cycle. All of you might have heard about Carnot cycle in your physics classes, those is in plus 2. But here, from a thermodynamic aspect, from a thermodynamic perspective, we will learn the Carnot cycle. So it was French military engineer Nicolas Sadi Carnot who studied the principles of second law of thermodynamics in detail. And he was the first to introduce the concept of cyclic operation and devised a reversible cycle comprising of 4 processes, 2 isothermal and 2 adiabatic process. And he named it as Carnot cycle. So here you can see 4 processes 1 to 2, 2 to 3, 3 to 4 and 4 to 1. 1 to 2 and 3 to 4 are isothermal or constant temperature process, and 2 to 3 and 4 to 1 are adiabatic process. A reversible adiabatic process is also known as isentropic process, where entropy is constant. So all these 4 processes are reversible. So this is shown on a pressure volume chart. Now let us see the 4 different processes in detail. Process 1 to 2 is reversible isothermal heat addition at a higher temperature, right, TH. So in that case, the cylinder head will be placed in contact with the source at a temperature TH, so that there is no temperature variation. There is no temperature variation, and the heat will be absorbed, or the heat will be supplied from a high temperature source to the cylinder gas at temperature TH. In order to maintain the temperature constant, the cylinder is made in contact, kept in contact with the high temperature source. So expansion is taking place and there is some boundary work W34. Further, the piston moves down inside the cylinder, but during that process, the cylinder is completely insulated so that there is no heat transfer. There is no heat transfer and making the constant adiabatic. So you have to remove the heat source which was in contact with the cylinder in the first process and maintaining a complete insulation to the cylinder, and the temperature will be changing from TH to TL. And again in the third process, which is a compression process, the piston will start moving upwards isothermally in order to maintain the temperature constant during the heat rejection process, that is at TL. The cylinder is made in contact with a low temperature sink, which is at temperature of TL. So where we need to give some work input, compression. Again, further the movement of the piston towards the top is processed as adiabatically, where the heat transfer is 0, by keeping the cylinder isolated from the surroundings so that the heat transfer is 0. And the temperature again is bringing back to TH from TL. I hope the 4 processes are clear. If you have any doubts, please rewind and see it again. Still, if you are not understood, please feel free to contact me. So from the thermodynamic point of view, let us analyze the Carnot cycle based on first law of thermodynamics. So 1 to 2 is a reversible isothermal process. reversible constant temperature process that is known as isothermal process. We can apply the first law of thermodynamics and write Q1, that is at point 1, the heat supplied is equal to U2 minus U1 plus W12, right? Or you can write it is a heat transfer Q. There is not a point function, it is a path function. It will be Q12. It will be Q12. Now let me change it, just a minute. So let us call that heat transfer as heat transfer at higher temperature QH instead of Q12 in order to avoid the confusion. And process 223 is reversible adiabatic process or isentropic process where heat transfer is 0. When we apply the first law, we can write U3 minus U2 plus W23. And the third process is again isothermal compression process where the heat is rejected, which is of the amount QL. Then reversible adiabatic process, the last process, which will bring back the system to the initial state 1. Again, you can write that as 0 equal to U1 minus U4 minus W4 1 because heat transfer is 0. Now combining all these, and from the fact that for a cyclic process the net heat transfer is equal to net work transfer, you can write QH minus QL is equal to W12 plus W23 minus W34 plus W41. The sign conventions are incorporated depending on the flow in or out of the system. If you have any doubts on the sign conventions, please refer to the first classes in thermodynamics. So a Carnot heat engine is a hypothesis. So that is the analysis for the Carnot cycle. Now coming to the Carnot heat engine, it is a hypothetical engine. It is an ideal with which we can compare the performance of all other engines which are operated in any other cycles. So we know that the thermal efficiency which we have seen in the earlier classes is equal to QH minus QL by QH or 1 minus QL by QH. So since the Carnot heat engine is reversible, we can write QL by QH is proportional to TL by TH from the thermodynamic temperature scale. So this is known as Carnot efficiency and is the highest efficiency that a heat engine can have while operating between TH and TL. This is the highest efficiency an engine can have. The temperature should be used when you use this equation should be expressed in Kelvin, not in Celsius. So if you see the equations carefully, you can see that the Carnot heat engine's efficiency increases as TH increases or TL is decreased. But there is a limit for the TL to be decreased, that is absolute 0. The thermal efficiency of actual heat engines can be maximized by supplying heat to the engine at a highest possible temperature. So we can supply the heat QEH to an engine at a very high temperature and rejecting heat at a lowest temperature possible. Thereby we can increase the efficiency, thermal efficiency of any heat engine. Now since we have said all the processes in a Carnot cycle are reversible, we can reverse all the processes like this. Instead of proceeding in a clockwise manner, we can proceed in an anti-clockwise manner. Thereby we can have a reversed Carnot cycle with which we can have a refrigerator or heat pump. the performance of a refrigerator or heat pump are usually expressed in terms of coefficient of performance instead of thermal efficiency, or the COP is nothing other than QL, or the desired effect divided by the work input. So there is a separate session. If you search for the channel for refrigerator and heat pump, you can see in detail all these terms. There are various important terms associated with refrigerator and heat pump. You can listen to that lecture and come back here again to see these derivations. Now, this is very important principles known as Carnot principles. For that, you have to consider heat engines, different heat engines operating between the same temperature levels TL and TH, lower temperature TL and higher temperature TH. Okay, so we can draw two conclusions about the thermal efficiency of a reversible and irreversible heat engines. So heat engines could be reversible or irreversible. Okay, so when you compare the efficiencies of reversible and irreversible heat engines, the two important conclusions listed here are termed as Carnot principles. The first one is the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between. The condition is that it should be operated between the same temperature limits TH and TL. The efficiencies of all reversible heat engines operating between the same two constant temperature heat reservoirs are the same. Suppose there are two separate heat engines, both are reversible. Okay, both are reversible, but I mean they can have different type of components, different make components, but if they are operating between the same temperature levels, the efficiencies of them will be the same. So these two are known as Carnot principles. So we can see the conclusion here. There is a high temperature source at TH and a low temperature sink at TL. The heat engine 1, HE1 is reversible, HE2 is reversible, and HE3 is also reversible. Okay, 2 and 3, second and third heat engines are reversible, and the first one is irreversible. So from the Carnot principles, you can see that the efficiency of heat engine 2 and 3 are the same, as well as the efficiency of heat engine 2 as well as 3 are higher than the thermal efficiency of heat engine 1. So as a result of the above, Lord Kelvin in 1848 used energy as a thermodynamic property, which we have already seen in the first law of thermodynamics, to define temperature, and devised a temperature scale known as thermodynamic temperature scale. And he concluded that the efficiency of any reversible heat engine could be expressed as a function of temperature alone, the temperature of high temperature and low temperature reservoirs alone. Thermal efficiency of a heat engine is a function of TH and TL alone. Thereby you can write efficiency of a Carnot heat engine as we have expressed 1 minus TL by TH. So that's all for today's session. If you have any doubts, please revert. Thank you for watching. Please share with your friends. We will meet with another interesting session. Till then, goodbye.